Today, we'll end up talking about a verified range analysis for JavaScript JITs, but we're going to work up to that by first discussing browser JITs themselves. Browser JITs live in your browser, Chrome, Firefox, Safari, whatever, and compile and execute all the JavaScript on every web page you visit. As a result, they're clearly on the critical path for good browser performance. This means that JIT architectures have evolved to be pretty complex, and the JIT code itself has to be pretty optimized too. The speed requirement, though, is in tension with security requirements in the JIT. Remember that the JIT has to compile any piece of JavaScript on the internet, any JavaScript, potentially adversarial JavaScript. So every compilation in the browser is security critical, because if the JIT has a bug in it, attackers can craft JavaScript whose whole purpose is to be miscompiled, and miscompiled in a way that lets attackers get remote code execution on victim machines. This actually happens too. On May 30th, 2019, employees of Coinbase were targeted with a phishing campaign that sent them to a web page that included malicious JavaScript. JavaScript targeting a bug in the JIT. It can be way worse than just Coinbase, too. Coinbase. In 2019, attackers used a JIT bug, among others, to install spyware on machines that navigated to, quote, websites that focus on content related to the Uyghur community. That's terrifying. So how do these exploitable bugs happen? A lot of different ways, so I'm just going to focus on bugs in the JIT's range analysis, an information gathering compiler pass that the compiler uses to inform other optimizations. Range analysis answers the question, what range of values can a variable take on at a given program point? In this example, at the yellow program point, range analysis says that x is between 4 and 100 and y is always 300. Range analysis can introduce exploitable bugs in the following way. First, since JavaScript is a memory-safe language, the JIT has to generate bounds checks to preserve memory safety. So we have this snippet of JavaScript that's doing a memory access. The compiler is going to add a bounds check to make sure the access of ARR at x is within bounds. But these bounds checks can get pretty expensive, so the compiler is going to use range analysis to eliminate them. Range analysis tells the JIT that x is 4, always in bounds on this path, so it can eliminate the bounds check. That means, though, that if range analysis is wrong, attackers can exploit the bug to access memory out of bounds. Let's say somehow range analysis got confused here. X is actually 4,000, but the range analysis mistakenly believed it was 4. Now, because range analysis gave bounds check elimination wrong information, BCE eliminates the bounds checks. Now an attacker can access ARR at index 4000, which is way out of bounds. This is what we want to prevent. But before we can figure out how to prevent it, we have to have some sense of how the browser implements range analysis. So let's check out the browser. Here we are in the browser, looking at part of Firefox's range analysis. It keeps track of ranges using this range class. And the important part of this, for our purposes, is right down here, where they keep track of upper and lower bounds on ranges. So if x is 4 at a program point, say, both lower and upper will be 4. But there's a whole bunch more stuff, right? And that's because JavaScript values are floating point values, so the ranges the JIT has to keep track of are floating point ranges. The browser keeps track of whether this floating point range actually is representable by an int32, if so it can do some optimizations, as well as keeping track of if the range can contain fractions or -0, etc. So imagine if a value could be either -0 or 0.5 at some program point. In that case, the -0 flag would be 1 because -0 is within the range at that program point. And the can't have fractional part flag would also be 1 because 0.5 is also within the range at that program point. So now let's go back to these slides to see a recap of all the flags that we care about in this range analysis object. Lower and upper are set if the range is representable by an int32, and the hasInt32 say whether the range can be represented that way. We talked about -0 and fractional parts, and finally, max exponent is the largest floating point exponent needed to represent the maximum absolute value in the range. We're not going to talk much more about that because it's kind of complicated. Alright, so now that the browser has this range analysis object, it can implement range analysis functions for each JavaScript operator. Here we are back in the browser with the range analysis routine for JavaScript's bitwise AND. This routine takes two ranges as input, LHS and RHS, and outputs a new range. If either one of the ranges can include a negative, it lower bounds the range with the minimum and 32 value. Otherwise, it does some calculation to determine an upper bound and then returns a new range. We really want range analysis routines to be right, so we're going to try and verify them correct. And how can we verify them? By asking if, according to JavaScript semantics for a given operator, it's possible to get a value outside the computed range for that operator. We're going to ask this question mechanically. So first, we'll encode JavaScript semantics for a given operator, like bitwise add, in SMT. Then, we'll encode the range analysis routine for that operator, again in SMT. But here's the routine we just saw for bitwise and it seems like it would be pretty gnarly to encode by hand. So, inspired by projects like Alive and Cobalt, at this step, we'll automatically generate the SMT from the C++ source code. And then, finally, we're going to ask the solver, is it possible to get a JavaScript value outside the computed range? For now, let's just assume that the SMT solver can magically do this for us and look at steps 1 and 2. Then we'll come back to step 3 in great detail at the end. So let's do it. And let's do it for ceil, the JavaScript operator for rounding up to the nearest integer. If you give ceil 0.5, for example, it's going to give you back 1. First, we're going to encode ceil's JavaScript semantics in SMT. It's pretty easy. If the number is already a 32-bit int, we just return it. Otherwise, we use an SMT sealing operator and return the result. Next, we're going to generate some SMT from the ceil range analysis routine. Here's the ceil range analysis from the browser, rewritten in our slightly more restrictive C++ dialect. It updates the rough upper bound by bumping up max exponent. Then, because ceil rounds up to a whole number, it clears the can have fractional part flag. Our tool, Vera, now compiles this C++ routine into SMT. Here's a little AST that it makes. Then it uses that AST to generate some SMT. Here's the generation code for numbers, calls, binary operators, etc. Alright, so now we have an SMT expression for ceil's semantics and an SMT expression for ceil's range analysis routine. To answer this third question, we have to connect those two things somehow. We need to relate JavaScript values to ranges. And to do that, we define this in-range predicate. The predicate returns true if a given value is within a range and false otherwise. For example, it will return false if the value is -0, but the range's has -0 flag isn't set. Or if the value is 0.5, but the range's can have fractional part flag isn't set, etc. You can think about the in-range predicate as basically encoding the logic in Firefox's range analysis object. There are a bunch of parts to this predicate in real life, because Firefox's range analysis object is pretty complicated. Here are all the different parts, and they're in the paper too. We're going to use the in-range predicate to prove that the browser's range analysis routines conform to JavaScript semantics. It'll take a few steps. First, we set up this equation that endval equals JSCeil of startval. So if startval is 0.5, endval is 1. Then, we're going to say that endRange is the result of ceil's range analysis on the start range. So in this case, this range coming in is the start range, and this returned range is the end range. Finally, we need to connect the values and the ranges using the in-range predicate. We're going to assert that the start value is within the start range. We're going to assume, in other words, that the previous step of range analysis went okay. Then we'll ask the solver, is it possible to get an endval that's outside the computed end range? In other words, is it possible for range analysis to be wrong? And this could happen, say, because of fractions or -0. In fact, any one of these conditions, infinity, nan, -0, fractions, could violate lower bounds or upper bounds. Any one of those things would be bad. And it turns out the ceil range analysis routine I showed you before is wrong. It's wrong for values between -1 and 0 exclusive, because JavaScript semantics says that ceil of a small negative is -0, not +0. The code for the ceil function, though, never sets the can be -0 flag. It definitely messes with the max exponent and the can have fractional part flag, but never with -0, right? And the solver is able to detect this. After we run it, it says that start is this small negative value, and that the start range doesn't include -0. Fine so far. The result of ceil on this small negative value is -0, still okay, but the result range doesn't include the can be -0 flag. It doesn't set that flag. This is clearly wrong. If the result is -0, the result range should include -0. Here's the result plugged into our proof template from before as another way of understanding what went wrong. And you might say, oh, -0, what's a little -0 between friends? But here's a blog post about how to use a similar bug in the Chrome browser to get remote code execution. It's a really interesting attack and worth a read. With that, we're done, so I'm going to quickly summarize our results. We wrote a tool called Vera that browser developers can use to verify their range analysis routines. We attempted to verify 21 range analysis routines in the Firefox browser, and including the entire in-range predicate and another predicate I didn't cover, this meant trying to verify 159 conditions, of which we proved or refuted 86%. We discovered one bug, the ceil bug that I showed you, that's existed for over 6 years in the browser, and when we ported Firefox's range analysis routines to Vera C++, we found no performance or functionality regressions. Finally, I'd like to shout out some cool work in the compiler correctness area. Browsers really scare me, and I think the more we can bring this sort of existing work into browsers, the better. I'd also like to give a big thank you to SMT solver developers. We use Z3 for this project, but have used other solvers for others, and every time we've dealt with the most responsive, helpful people making great tools. So thanks. Anyway, here's a recap of what I talked about, and I'm happy to take questions. Thanks so much.